The material entering the facility originates from wholesale fruit markets, food processing centers, and municipal organic waste collection points, where durian shells are accumulated in large volumes after the edible pulp has been removed. These shells are bulky, fibrous, moisture-rich, and naturally resistant to rapid decomposition, which historically made them difficult to manage through conventional waste systems. The modern recycling facility is designed specifically to address these characteristics at industrial scale, transforming what was once an environmental burden into a usable resource stream through a sequence of mechanical, thermal, and biochemical processes. Upon arrival at the facility, incoming loads are first weighed and logged to establish material flow data. This information is critical for monitoring throughput, optimizing machine utilization, and maintaining consistency in output quality. The shells are then unloaded onto reinforced receiving platforms, where visual inspection removes obvious contaminants such as plastic packaging, metal fragments, or residual fruit crates, although upstream suppliers are encouraged to pre-sort. The facility assumes a margin of contamination and incorporates redundancy in its separation systems to ensure process reliability. The initial mechanical stage focuses on size reduction. Crayon shells are structurally tough, with thick husks composed of lignocellulosic fibers and sharp outer spines. Industrial shredders equipped with hardened steel blades and high-torque motors break the shells into manageable fragments. This step is essential not only for downstream handling, but also for increasing surface area, which improves efficiency in subsequent drying, extraction, or conversion processes. Blade geometry and rotational speed are carefully calibrated to avoid excessive fines while ensuring consistent fragment size. Following shredding, the material enters a washing and cleaning phase. High-pressure water jets and rotating drums remove residual pulp sugars and soil particles that could interfere with further processing or promote microbial instability. Wastewater generated at this stage is collected and treated on-site using sedimentation and biological treatment units, allowing water to be reused within the facility and minimizing discharge. Takeda's closed-loop approach reduces overall water consumption and aligns with environmental compliance standards. Moisture management is a critical challenge in durian shell recycling. Fresh shells contain a high percentage of water, which increases weight, reduces energy efficiency, and limits storage stability. After washing, the material passes through mechanical dewatering systems such as screw presses or belt presses, which remove free water through compression. The partially dried material is then transferred to thermal drying units. These may include rotary dryers or conveyor-based drying tunnels, where controlled heat and airflow reduce moisture content to a target range suitable for further processing. Energy for drying is often recovered from waste heat generated elsewhere in the facility, improving overall energy efficiency. Once dried, the shells become a versatile intermediate material. At this stage, the facility may divert the processed shells into multiple production lines depending on market demand. One common pathway involves conversion into biomass fuel. The dried shell fragments are milled into smaller particles and compressed into pellets or briquettes using high-pressure extrusion equipment. These biomass products offer a renewable energy source with relatively stable calorific value and can be used in industrial boilers or power plants as a partial replacement for fossil fuels. Another significant utilization route focuses on material extraction. Durian shells are rich in cellulose, hemicellulose, and lignin, making them suitable for producing bio-based materials. In this pathway, the dried shells undergo further milling to achieve a fine, uniform particle size. Chemical or enzymatic treatments may then be applied to separate cellulose fibers from lignin components. The extracted cellulose can be used in the manufacture of biodegradable packaging, composite materials, or as a reinforcing fiber in construction panels. Lignin byproducts may be repurposed as binders, additives, or energy feedstock. Some facilities integrate a biochemical processing line aimed at producing activated carbon or absorbent materials. In this process, the shells are subjected to controlled pyrolysis in oxygen-limited environments. High temperatures drive off volatile compounds, leaving behind a porous carbon structure. Subsequent activation using steam or chemical agents increases surface area, producing activated carbon suitable for water filtration, air purification, or industrial adsorption applications. Process parameters such as temperature, residence time, and activation method are precisely controlled to achieve consistent pore structure and adsorption capacity. Quality control is embedded throughout the production chain. Sensors and sampling stations monitor particle size distribution, moisture content, chemical composition, and calorific value, depending on the end product. Data from these monitoring systems feeds into centralized control software, allowing operators to make real-time adjustments and maintain product specifications. This level of automation reduces variability, minimizes waste, and improves overall yield. Environmental management is a central design principle of the facility. Dust generated during shredding and milling is captured through filtration and cyclone separation systems, preventing airborne emissions and maintaining worker safety. Odor control systems, including biofilters and activated carbon scrubbers, address the naturally strong smell associated with durian waste, ensuring compliance with local environmental regulations and minimizing impact on surrounding communities. From an economic perspective, the recycling operation demonstrates how agricultural waste can be integrated into circular economy models. By converting discarded shells into energy, materials, or chemical feedstocks, the facility creates value streams that offset operational costs. Long-term supply agreements with fruit distributors stabilize input availability, while diversified output products reduce exposure to market fluctuations in any single sector. Labor within the facility is a combination of skilled technical operators, maintenance personnel, and quality control specialists. While much of the process is automated, human oversight remains critical for equipment maintenance, troubleshooting, and process optimization. Training programs emphasize safety, particularly given the mechanical hazards of shredding equipment and the thermal risks associated with drying and pyrolysis systems. Logistics and storage also play a crucial role. Dried intermediate material is stored in climate-controlled silos or warehouses to prevent moisture reabsorption. Finished products are packaged according to customer requirements, ranging from bulk shipments for industrial users to smaller, standardized units for commercial distribution. Inventory management systems track product movement and ensure traceability from raw shell intake to final output. The broader impact of such a facility extends beyond waste reduction. By diverting durian shells from landfills, methane emissions associated with anaerobic decomposition are significantly reduced. The substitution of biomass fuel for fossil fuels contributes to lower net carbon emissions, while bio-based materials decrease reliance on petroleum-derived plastics and chemicals. These environmental benefits are increasingly quantified through life cycle assessments, which help demonstrate compliance with sustainability targets and attract investment. Technological innovation continues to refine the recycling process. Research partnerships with universities and material science institutes explore improved extraction methods, higher value applications for shell components, and more energy-efficient processing techniques. Advances in enzyme technology, for example, promise more selective cellulose extraction with reduced chemical usage. Similarly, improvements in sensor technology and machine learning algorithms enable predictive maintenance and further optimization of process parameters. Regulatory frameworks influence facility design and operation. Waste classification standards, emissions limits, and product safety regulations dictate process controls and documentation requirements. Compliance is maintained through regular audits, reporting, and continuous monitoring. In regions where durian production is concentrated, supportive policies and incentives for waste valorization can accelerate adoption of such recycling technologies. The facility also serves as a demonstration of scalability. Modular processing units allow capacity to be expanded as input volumes increase or new product lines are introduced. This flexibility is particularly important in agricultural contexts, where seasonal fluctuations in waste availability are common. By adjusting operating schedules and storage strategies, the facility maintains year-round productivity despite variable input flows. In summary, the modern durian shell recycling factory represents a sophisticated integration of mechanical engineering, chemical processing, environmental management, and economic strategy. Through systematic handling of a challenging organic waste stream, it converts discarded shells into valuable resources while reducing environmental impact. The operation illustrates how targeted industrial design and technological innovation can transform niche agricultural byproducts into components of a broader sustainable materials and energy ecosystem.